Welcome to our journey into the world of units and measurements. In physics, understanding how we measure and describe the world around us is fundamental. This chapter lays the foundation for all scientific study by explaining what physical quantities are, how we measure them, and why standardization is crucial. Whether you're new to physics or brushing up on the basics, this video will guide you through key concepts, from the definition of physical quantities to the importance of accuracy and precision. Let's dive in and explore how measurements form the backbone of scientific discovery. Physical quantity is any property of a material or system that can be measured and expressed with a number and a unit. For example, length, mass, and time are all physical quantities. These quantities help us describe the physical world in a precise and standardized way. Without physical quantities, it would be impossible to communicate scientific ideas clearly or compare results from different experiments. Understanding what physical quantities are is the first step in mastering measurements in physics. Physical quantities are divided into two categories: fundamental and derived. Fundamental quantities are basic and independent, such as length, mass, and time. These cannot be broken down into simpler quantities. Derived quantities, on the other hand, are formed by combining fundamental quantities according to physical laws. For example, speed is a derived quantity because it is calculated as distance divided by time. Recognizing the difference between these two types is essential for understanding how measurements work in physics. International System of Units, or SI units, is the globally accepted standard for measurement in science. SI units provide a consistent way to express physical quantities, making it easier for scientists worldwide to share and compare results. The system includes 7 base units, such as the meter for length, kilogram for mass, and second for time. Using SI units ensures clarity and uniformity in scientific communication. Standard units are essential because they allow scientists and engineers to communicate measurements accurately and reliably. Without standard units, comparing results from different experiments or locations would be confusing and error-prone. Standardization eliminates ambiguity and ensures that everyone is speaking the same scientific language. This is why SI units are so widely adopted in the scientific community. Dimensional analysis is a powerful tool in physics that helps us check the consistency of equations and convert units. By analyzing the dimensions of physical quantities involved in an equation, we can verify if the equation makes sense. For example, if both sides of an equation have the same dimensions, the equation is likely correct. Dimensional analysis is also useful for converting between different units and solving complex problems. One of the main uses of dimensional analysis is to check the correctness of physical equations. By ensuring that both sides of an equation have the same dimensions, we can catch mistakes before they lead to incorrect results. For instance, if you have an equation for speed, the dimensions should be length divided by time on both sides. This simple check can save a lot of trouble in scientific calculations. While dimensional analysis is a valuable tool, it does have its limitations. It cannot provide information about numerical constants or the specific form of an equation. Also, it cannot distinguish between quantities with the same dimensions but different physical meanings. Therefore, while dimensional analysis is useful for checking consistency, it should not be the only method used to validate equations. Accuracy and precision are two important concepts in measurement. Accuracy refers to how close a measured value is to the true value, while precision describes how close repeated measurements are to each other. For example, if you weigh an object several times and get similar results each time, your measurements are precise. If those results are also close to the actual weight, they are accurate. Both accuracy and precision are essential for reliable scientific measurements. Errors in measurement can be classified as systematic or random. Systematic errors are consistent and repeatable, often caused by faulty equipment or flawed methods. These errors can be corrected once identified. Random errors, on the other hand, are unpredictable and vary from one measurement to another. They arise from unpredictable fluctuations in experimental conditions. Understanding the difference helps in improving measurement techniques and achieving more reliable results. The least count of an instrument is the smallest value that it can measure accurately. For example, a ruler with millimeter markings has a least count of 1. The concept of least count is important because it determines the precision of your measurements. Always be aware of the least count when recording data, as it sets the limit for how finely you can measure with a given instrument. Errors are an unavoidable part of any measurement. To calculate error, you compare the measured value to the true or accepted value. The difference between these values gives you the error. Understanding how to calculate and interpret errors is crucial for evaluating the reliability of your results and improving your experimental techniques. Absolute error is the difference between the measured value and the true value of a quantity. It gives you an idea of how much your measurement deviates from the actual value. Absolute error is always expressed as a positive number and is a straightforward way to quantify the accuracy of a measurement. Relative error is the ratio of the absolute error to the true value, often expressed as a fraction or percentage. It provides a sense of how significant the error is in relation to the size of the measurement. Relative error is especially useful when comparing the accuracy of measurements with different magnitudes. Percentage error is another way to express the accuracy of a measurement. It is calculated by dividing the absolute error by the true value and multiplying by 100. This gives you a percentage that shows how large the error is compared to the actual value. Percentage error is commonly used in scientific reports to quickly convey the reliability of results. When adding or subtracting measured quantities, the absolute errors are added together to find the total error. This means that the uncertainty in the result is the sum of the uncertainties in each measurement. Being aware of how errors combine helps you report results more accurately and understand the limitations of your data. For multiplication and division, the relative errors of the measured quantities are added to find the total relative error in the result. This approach ensures that the final uncertainty reflects the combined effect of all measurements involved. Understanding this rule is key for handling complex calculations in physics. Significant figures are the digits in a measurement that carry meaning about its precision. They include all certain digits plus one uncertain digit. The concept of significant figures helps you communicate the reliability of your measurements and avoid overstating the accuracy of your results. There are specific rules for determining which digits in a number are significant. All non-zero digits are always significant. Zeros between non-zero digits are also significant. Leading zeros are not significant, but trailing zeros in a decimal number are. Knowing these rules ensures you report measurements correctly and consistently. Significant figures are crucial in physics because they reflect the precision of your measurements. Reporting too many digits can give a false impression of accuracy, while too few can hide important information. Using the correct number of significant figures ensures your results are both honest and useful. Measurements are at the heart of physics. Every physical law and theory is based on careful observation and measurement of the natural world. Accurate measurements allow scientists to test hypotheses, develop new theories, and advance our understanding of the universe. Without reliable measurements, physics would not exist as a science. Let's look at more examples of physical quantities. Besides length, mass, and time, other fundamental quantities include electric current, temperature, amount of substance, and luminous intensity. Derived quantities, such as velocity, force, and energy, are built from these basics. Recognizing these helps you understand the wide range of phenomena physics can describe. The 7 SI base units are meter length, kilogram mass, second time, ampere electric current, Kelvin temperature, mole amount of substance, and candela luminous intensity. Each unit is precisely defined to ensure consistency worldwide. Mastering these units is essential for any student of science. Derived units are created by combining base units according to physical laws. For example, the unit of force is the Newton, which is defined as kilogram meter per second squared. These derived units make it easier to express complex physical relationships in a standardized way. SI units are preferred in science because they are universally accepted and based on precise definitions. This makes scientific communication clear and reduces the risk of errors. Using SI units also simplifies calculations and ensures that results can be easily compared across different studies and countries. Dimensional formula expresses a physical quantity in terms of the base quantities. For example, the dimensional formula for velocity is LT1, where L stands for length and T for time. Dimensional formulae help in understanding the relationships between different physical quantities and in checking the validity of equations. In practice, dimensional analysis is used to convert units, derive relationships between quantities, and check the plausibility of equations. For example, if you know the dimensions of force and acceleration, you can deduce the dimensions of mass. This technique is a valuable problem-solving tool in physics. An equation is said to be dimensionally homogeneous if all terms have the same dimensions. This is a basic requirement for any physical equation. Dimensional homogeneity ensures that the equation is physically meaningful and can be used reliably in calculations. Imagine you are throwing darts at a target. If all your darts land close to the bullseye, you are accurate. If they land close together but far from the bullseye, you are precise but not accurate. If they are scattered, you are neither accurate nor precise. This analogy helps clarify the difference between these two important concepts in measurement. Systematic errors can be minimized by calibrating instruments, using proper techniques, and regularly checking equipment. Identifying and correcting these errors is essential for improving the accuracy of your measurements and ensuring reliable results in experiments. Random errors can be reduced by taking multiple measurements and averaging the results. This approach helps to cancel out unpredictable fluctuations and provides a more reliable estimate of the true value. Consistency in experimental conditions also helps minimize random errors. Calibration is the process of adjusting an instrument to ensure its readings are accurate. Regular calibration is necessary to maintain the reliability of measurements, especially in scientific research and industrial applications. Proper calibration helps eliminate systematic errors. When reporting measurements, always include the unit and the correct number of significant figures. This practice ensures that others can interpret your results accurately and understand the precision of your data. Clear reporting is a hallmark of good scientific practice. Every measurement has some uncertainty, which reflects the limitations of the measuring instrument and the method used. Expressing uncertainty alongside your results helps others understand the reliability of your data and the possible range of values. In performing calculations, the number of significant figures in the result should reflect the least precise measurement used. For addition and subtraction, the result should have the same number of decimal places as the least precise value. For multiplication and division, use the same number of significant figures as the measurement with the fewest significant figures. Suppose you measure a length as 12.3 cm and another as 4.56 cm. When adding, your result should be reported to one decimal place, matching the least precise measurement. This rule prevents overstating the accuracy of your results and maintains consistency in scientific reporting. Measurement errors can have significant real-world consequences. For example, small errors in engineering measurements can lead to structural failures, while errors in medical measurements can affect patient safety. This highlights the importance of careful measurement and error analysis in all scientific and technical fields. Measurement standards are established references used to calibrate instruments and ensure consistency across different laboratories and industries. International organizations maintain these standards to guarantee that measurements are reliable and comparable worldwide. Traceability means that a measurement can be related to national or international standards through an unbroken chain of comparisons. This ensures that results are reliable and can be reproduced anywhere in the world. Traceability is a key principle in scientific and industrial measurements. Units play a vital role in scientific communication. They provide context for numerical values and ensure that everyone interprets measurements in the same way. Always include units when reporting data to avoid confusion and misinterpretation. Measurement systems have evolved over time, from ancient units based on body parts to the highly precise SI system we use today. This evolution reflects humanity's growing need for accuracy and consistency in science, trade, and daily life. We use measurements every day, from cooking recipes to measuring distances while traveling. Understanding units and measurements helps us make sense of the world and make informed decisions in daily activities. Measurement science continues to advance, with new technologies enabling even greater precision. From quantum standards to digital instruments, the future promises more accurate and reliable measurements, driving progress in science and technology. Let's recap what we've learned. Physical quantities are measured using standard units, and accuracy, precision, and error analysis are vital for reliable results. Dimensional analysis helps check equations, and significant figures ensure honest reporting. Mastering these basics is essential for success in physics and beyond. In conclusion, units and measurements are the foundation of all scientific inquiry. They allow us to describe, understand, and innovate in the world around us. By mastering these concepts, you are taking the first step toward becoming a skilled scientist or engineer. Keep exploring, measuring, and discovering.